In this lecture, we're going to look at the idea of convergent matrices. Let's start with the definition of what a convergent matrix is. Definition: a matrix A belonging to C cross N, C and cross N is said to be convergent if and only if limit k tends to infinity, a raised to k is equal to 0. So convergent matrices are very useful whenever we are dealing with optimization problems. So we have to check whether it converges, the problem converges to a solution. Then we have to look whether the matrix which we have as the kth step of the sequence is actually convergent. So how do we check that if a matrix is actually convergent? So for that we have a lemma. We've already seen a condition for vector norms. How can we say whether? Discuss this briefly also whenever we're discussing the inverse of 1 plus x, I suppose, or 1 minus x. Yeah, 1 minus x. 1 minus x whole inverse. We discuss that. Okay, we'll discuss that in more detail. Anyway, then moving forward. Let's look at this lemma first. Lemma states that let A belong to C n cross n if there is a matrix norm which is given by 3 bars such that with respect to that matrix norm, if the norm of A is less than 1, then excuse me, then A is convergent. Or how do you write convergence? Limit k tends to infinity. If k is equal to 0. Okay. How do you prove this? The proof is actually very easy. How can we prove this? Proof. So norm of A is less than 1, right? Yeah. If norm of A is less than 1, what about norm of A squared? Norm of A squared will be less than or equal to norm of A into norm of A, which is less than or equal to norm of A whole squared. But since norm of A is less than 1, norm of A squared will be also less than 1. In a similar fashion, we can extend norm of A, k, it will be less than or equal to norm of A raised to k, as norm of A is less than 1, norm of A, k, norm of A raised to k will be also less than 1. Right? Yeah, this will be also less than or equal to 1. And therefore, norm of a raised to k will be also less than or equal to 1. Right? And norm of a raised to k tends to 0 as k tends to infinity. The standard result for sequence with modulus magnitude 1, this will tend to infinity. Okay, but we have seen that norm of ak tends to infinity. Does it mean that a tends to infinity? Yes, because if simplest way is to use positivity. By positivity, if norm of a tends to 0, a should tend to 0. Right? This is a 1AF because it's a valid norm. That's the positivity condition. So if ak tends to 0, norm of ak tends to 0, a raised to k tends to 0, then a raised to k tends to 0 implies every element of ak should tend to 0. Okay. So this is how we can prove this. And there's also another condition which we can write for convergence. Let's look at the second lemma. This actually is like a complementary lemma, which follows from this. This is very simple to derive also. It's like this lemma. Let A be our square matrix or the field C. Then limit x tends to infinity, sorry, k tends to infinity. A raised to k is equal to 0 if and only if the spectral radius is less than 1. This is actually intuitive. From the earlier case, we've already proved that if norm of A is less than 1, then we'll prove this systematically, but before that, let me try to give the intuition. We know that rho of A is actually less than or equal to norm of A, right? And also, this is the lowest upper bound. So lowest, greatest lower bound. So this is arbitrarily close to norm of A. This is norm of rho of A plus epsilon, like this. So if rho of A is less than 1, we can find an arbitrary close rho A this epsilon which is less than 1, then can say this x is some norm, vector norm, which is actually less than 1. And this is actually the previous condition. And this is how we are proving this. Okay. So this is if rho of A is less than 1, we can prove that this is convergent. So from this lemma, if norm of A is less than 1, then limit k tends to infinity, a k is equal to 0. This is one way of proving it. Right? Since it's an if and only if condition, we have to prove it the other way also. I don't know whether we proved all the if first. So here we are given this is only if. Okay, this is not if, this is only if. Now let's prove the if condition. In if condition, what we are given is a raised to k tends to 0 as k tends to infinity. This is given, right? Then we have to prove rho of A will be less than 1. And let's do this. Let x be a non-zero eigenvector of A such that Ax is equal to lambda x and x not equal to 0. In such a case, what can we talk about then? A raised to of not a raised to k. Then a raised to k into x is lambda raised to k x, right? Yeah. Now, what is given here is, since ak tends to 0, as a raised to k tends to 0, a raised to kx also will tend to 0, implies lambda k x. This also tends to 0. Right? And lambda k, okay, this implies lambda k tends to 0 as k tends to infinity. So we have a quantity that tends to 0 as k tends to infinity. This happens if, only if, modulus of lambda is less than 1. If modulus of lambda is less than 1, then the max of, this is for any lambda, max of lambda, or you can say, yeah, max of modulus of lambda, a lambda big N I vector will be also less than 1, because this is also an eigenvector. For any eigenvector, this should be satisfied. This implies the rho of A should be less than 1. So hence proved. We've proved if and we've proved only if. So both these conditions are proved. So convergence of a matrix can be satisfied in two ways. If one way is if we have a norm such that norm of A is less than 1, then A raised to k will tend to 0 as k tends to infinity. That is one way. And in a similar fashion, we can also find the spectral radius of a matrix A, and if the spectral radius of that is less than 1, we can say that this is a convergent matrix. There are two ways of defining convergence. Let's end this discussion.